We've been focusing on frequency domain modeling. Okay. Today we'll start with time domain modeling. Okay. And this will also be called state space modeling. Now keep in mind we've already looked at one type of time domain modeling, and that is the differential equations. I'm going to explain this to you with an example. The example will be the same. We looked at this, right? We looked at two masses and this is M1 M2. I think there was a spring, there was a damper here, and then there was a spring here. There's another spring here. K1, K2, K3. Then we said this is C2, C1. Okay. And we arrived at using impedance approach. We arrived at these equations. Okay. M S square plus or M1 S square plus C1 plus C2 S plus K1 plus K2. Right? This whole thing into x1 of S minus C3S plus K2. And let's not forget there was a force here, F of t, and this is the first displacement x1 of t. And this is the second displacement x2 of t equal to F of S. And it's going to write it this way. Let me see. Okay. Now, if you take the inverse Laplace transform, all right, what you're going to get is M1 double dot C1 plus C2 minus C3 x2 t minus k2 x2 t equal to f of t.
Seriously, can you put what the inverse of Laplace theorem, whatever formula is, or like what it is?
You can look at the table and figure that out. Okay, it's very simple. Let me hang on. Let me do that. Okay, let me show you. We have looked at this. Okay, I'm going to just open this up and show you how I got from here to here. All right, just pay attention here. You don't have to note this down. You need to learn this. You will do problems through which you learn this technique. It's very simple. So you have, what do you have? You have m1 s square x1 of s plus c1 plus c2 s into x1 of s plus k1 plus k2 minus c3s x2 of s minus k2 x2 of s equal to f of. You with me? I just took this first equation, and split it open. Okay? This x1 of s is distributed between these 4 terms or these 5 terms, and x2 of s is split between these 2 terms. Alright?
Dr. Cindy, that for M2, for the inverse Laplace, that's supposed to be K2 and K3? K2 and K3?
Yes. Okay. So I just took this and split it open. Alright? Now, what I'll do is, I'll take the inverse Laplace on both sides, right? Or the entire thing. So inverse Laplace of this is what? M1 x double dot x1 double dot of t. You got it? Simple. If there is a s square, this becomes x1 double dot plus. You see s, there is just one s, right?
So it'd be C1, C2, X1.
One dot. There is s. If there is s square, it is double dot. If it is s, there is single dot. There is no s here.
So it'd be
X1 of t. You got it? Okay. Minus, again, this will be C3
X2 dot
x2 dot of t.
K2X.
C2 x2 of t. Yeah. These two are representing the same system or part of the same system. This equation and this equation. This is in frequency domain. This is in time domain. Okay. The input here is what? Hmm?
Time. Is that what you're asking?
Time
Vari-
cannot be the input.
What the variable is?
Input. What is the input here?
Oh, the force.
Yeah, the force. Okay, f of t. So this force is the input, right? So you can express this force either as function of time, which is like this, or function of frequency like this. You understand? It's the same thing. Just one is expressed as time, one is expressed as frequency. All right. What is the output here?
You said the output. Displacement.
Mass.
Right. So it could be displacement, which is this. It could be velocity
Or acceleration.
or acceleration. All right. So here, this is acceleration term, right?
Hmm.
In terms of time. This is acceleration term in terms of frequency. You get it? This is velocity term in terms of time. This is velocity term in terms of frequency. This is displacement in terms of time. This is displacement in terms of frequency. That's all. All right. Now, I'm going to use this. For state space modeling, the idea is focus on this, okay? These two sets. And of course these two sets as well. Okay? So let's call this A. Let's call this B. Okay. What is the order of the system? How do you determine the order of the system?
The highest power.
Hmm?
The highest power.
Power, right? So here, what is the power of the polynomial? Here you look at the power of the polynomial.
Second.
2, right?
Yeah, second.
But there are two order, second order polynomials, right? In S square. So this is a fourth order system. You see that? So these two cannot be decoupled, okay? So these two together represent this system. Do you see this as a fourth order system? Correct? S square, right?
Mhm.
That makes it a second order system. Just the first equation. It's a second order polynomial. Okay. Together they make it a fourth order polynomial. And you can do that here as well. You see what is the order of the system? What kind of equation is this?
Which one? The bottom one?
Sign.
This right there.
Sign.
Now, what kind of equation is it? What kind of equation is this? Or what kind of relationship is this? What kind of expression is this?
Are you talking about the S terms and the X double dot terms?
When he's talking about expression, it's an expression.
What kind of equation is this? What kind of math equation is this?
Differential equation.
This one?
No, it's a, no, it's a, what is it called? Polynomial.
It's a polynomial. It's an algebraic equation. You see? You see that this is a polynomial or an algebraic equation? What about this one?
Differential.
Differential. This is calculus based, right? This is an ordinary differential equation. Do you see that? This is algebraic equation and this is differential equation. Okay. So now what we do is for state space modeling, an nth order differential equation gets transformed to n first order equations. Okay. We'll talk about this. So we introduce something called, we define something called states of the system. Okay. Let's define z1 equal to x1 of t, z2 equal to x1 dot of t. Okay. Similarly, z3 is x2 of t, z4 is x2 dot of t. These are the states. z1, z2, z3, z4 are states of the system. Okay. Now, we define something called state equations. Okay, this is the first step and this is the second step. State equations start with z1 dot is what? x1 dot, which is equal to z2. Okay. Similarly, z2 dot is what? x1 double dot which is equal to minus this can be slightly overwhelming. Okay, I would urge you to pay attention here.
So, actually,
Hmm.
so for that one, it seems like all you did is just solve for z double dot in the first equation, and you just divided your m1 over, like you moved everything.
Right. So what I did is z1 dot, okay, state equations start with the derivative of the state variables. z1 dot is equal to x1 dot, okay, z1 dot is x1 dot, but the x1 dot is z2. Alright. Similarly, z2 dot is x1 double dot, alright. I'm extracting this from here. x1 double dot is what? I take all of this on the right hand side. Alright. So if you look at that, it is minus 1 over m1 c1 plus c2 minus 1 over m2 m1 k1 plus k2, all that. The idea is to write it in the form of these state variables. So what is this? What is the state variable associated with? Keep in mind what are x1 dot, x1 double dot. Excuse me. What are these called? Any idea? I'm going to give it to you. These are called system variables. Typically, system variables have a physical meaning. Okay. What are the system variables here? What is the physical meaning of those system variables? Or what do you call them? What are the physical names?
Displacement, speed, acceleration.
Yes, displacement, velocity, acceleration. Okay. So these are the system variables. Now here, z1, z2, z3. Are state variables. Okay. Again, you can look at them as it's the same thing. Okay. The variable, it varies as a function of time. So the idea is state space modeling. The idea of state space modeling is to write everything in terms of state variables. So here what's going to happen is, what is the state variable associated with x1 dot of t? It is
Z2,
z2, right? This is
Z1,
z1. This is z4. This is so if I write it, I'm going to write z2 minus 1 over m1.
so you're changing your system variables to the state.
Right.
Oh.
z1. What I'm going to do is, yeah, and this is equal to, if I rearrange this,
That's still going to be equal to Z dot 2 though, right? That's still going to be equal to Z dot 2 though, right? Or does it change?
yes, yes. So if it will still be z, not z dot 2, it's z2 dot. Okay. minus 1 over m1 k1 plus k2 g1 minus 1 over m1 c1 plus c2 g2 plus c2 over m1 The order is Z1, Z2, Z3, Z4. Okay. Now,
So,
we'll do the same thing for.
Can I ask a question, Dr. Sen?
Yes.
Why are you dividing by state variables?
Where am I dividing?
Or so could you? Well, if you're not dividing, could you explain why you've got x1 dot t over z2?
He's just saying that's what he's
No,
doing.
he's
Oh,
saying-
okay, I got you. He's just replacing it.
So we had to change frequency to time so we could find out these system variables.
Gotcha. Okay.
You're not changing frequency to time. Now, keep in mind, the transition is frequency to time here. Okay. But you need these set of equations to go from here to here. Okay. So frequency to time and time to time.
So you can't go frequency to
You can, if you do it enough number of times. There is a way to do that, but this is the easier way. Okay. The math will be a little more complicated if you try to do that, but you can still do that. You don't need to do that. Just for now, just stick to this approach. All right. So here, what you're looking at is still not complete. Let me try to complete that. And try to keep this in mind. So my Z3, what would Z3 dot be? Any idea?
Z4.
Right. Okay, because Z3 dot would be X2 dot, right? X2 dot is Z4. So similarly, now Z4 dot is equal to,
0.
and I'll let you solve this yourself. It is not 0.
Why is it not 0?
It is minus 1 over M2.
Oh, okay.
Okay.
C2 plus C3 x dot 2.
Or let me try to write it like this. K2 over M2 Z1 plus C3 over M2 Z2 minus 1 over M2 K2 plus K3 Z3 minus 1 over M2 K2 plus K3 Z4. I need you to learn how to go from, so it's Z1, Z2, you know how you got it. This is very similar. You can do it on your own. Okay. Now, these four together, Z1, Z2 dot, you can write this as and again, see if this makes sense. 0, 1, 0, 0. This is minus 1 over m1 k1 plus k2 minus 1 over m1 c1 plus c2. K2 over m1 and c3 over m1. Okay. We have 0, 0, 0, 1. Then you have K2 over m2, C3 over m2 minus 1 over m2. Actually, a 1 over m missing here. Okay?
With the FFT?
Yeah.
Oh, yeah.
M1.
I was gonna
So I've taken these 4 equations 1, 2, 3, 4 and written it in a matrix form.
Jeez. What is
Okay. And there is I'm going to erase this. See if I can get you know all this. Right? Let me just do this. V1 dot V2 dot V2.
Do you want us to write this down, Dr. Sunny?
Hmm?
Do you want us to write what you're writing down?
As long as you have written down this, that's fine. Okay, I'm just moving this there.
Okay.
Okay, that is the reason I'm moving it. Talk about it. Just erase this. So let's call this for now 1, 2, 3, and this is 4. Okay. So you can say 1, 2, 3, 4 are state equations.
Okay. Good. Oh, sorry.
Hmm?
Never mind. Sorry, I was gonna ask what you meant. So I didn't see where you'd written 1 and 2.
Hmm?
I didn't see where you'd written 1 and 2. So.
1, okay, 2, 3, and 4 are state equations. Okay. Now we introduce something called output equation. So here, if we define, it depends on how you define your output. Okay. So you looked at output could be defined as, let's say if I define output as x1 of t and x2 of t. Okay. This output equation becomes y, which is the output, equal to 0, sorry. One, 0, 1, 0, 3, 1, 3, 2, 3, 3, for this output. Okay, guys, you both are going to lose attendance.
Oh, it's in this class too? Oh, did not know that.
It's in all of Dr. Ascendi's classes.
Yes, that makes sense. Yes.
This class you have lost attendance. Okay, so you have this. What is x1 of t in terms of state equation? It is z1, right? This corresponds to and this corresponds to z3. Okay, so you try to understand this. One, 0, 1, 0, and this entire thing is the same.
Will either of those matrices remain constant? Or will either of those matrices remain constant at the always or no?
These, depending on what your state variables are, so the general form of the state space model is you have, I'm going to write this equal to a z plus b u So what is this? So look at this. Okay? This is the general form of state space model of that same system. Z dot, this is this. You with me?
Mm-hmm.
A is this. This Z is this. B is this. U is this. Right now, it so happens that there is only one input, right? There can be multiple inputs, and this U can take a form like that. All right. Similarly, Y is this. It's the same, represented by output. C is this. Z is this. This we may not yet encounter this for this course. Okay.
Where is the 1 divided by M1 coming from the force of T? Why is it in second column?
It just
second.
So if you look at this, if I'm solving for x1 double dot of t, right? Get it? I think I have to write here as well.
Yeah. You just forgot to distribute it to the F2 as well when you divided it.
This one, okay?
No, I see that. I'm talking about this, that. The,
Yeah, so the 1 over M1, you see how you put all the things in matrices? That 1 over M1 is with F of T, so then it has to have its own matrices. It's the only one.
Yeah, no, I get that, bro. I'm saying why is that F of T right there in that just the second row? Why is that on the second row?
Right. We'll talk about that, okay? So this is the first row, right? You see this?
Mm-hmm.
You see Z1 dot is Z2, right? So if you solve for this, we want to get Z1 dot is 0 into this, right? Plus 1 into this, Z2. You got it?
Mm-hmm.
And rest is 0, right? For Z1, you solve for Z1 dot is this into this.
Right.
Plus 0 into f of t. Got it? That's the first equation.
Okay.
The second equation is Z2 dot is equal to minus this into Z1.
Okay.
Minus this into Z2, right? Plus K2M1 into Z3, this term, plus this term, plus you see 1 over M1 FT, right? 1 over M1 FT. This term will only add to equation 2. There is no FT, F of t anywhere else. Because of this, right? F of s only exists here, or F of t exists here only.
Right.
Okay, so if you solve for it, you'll get that.
Yeah, I see what you're saying. I was more or less. I see what you're saying, but I kind of get one. It's in 2. I thought it'd be in 1 and 2.
No, it is not. If you look at here, this is the first equation, right?
Mm-hmm.
So there is no f of t. It's the format of the set of equations. That's what I understand what you're trying to say, but it's the how you develop them.
Okay.
It depends on that. Okay. Now, what I want you to understand is, you saw this physical system, or not the physical system, but the free body diagram of a system, right? Here. Before, when we started this whole thing. You saw a spring mass damper system? You remember? You have in your notes? The block diagram or the free body diagram, you saw that, right? That system, the mathematical model of that system could be this, which is a Laplace transform model, could be this, which is a differential equation model, or could be this, which is a matrix model. All these three, so we'll call this as C. A, B, C. You need to understand how to model these systems mathematically. It's a big part of your course. Okay, specifically this one and this one. You have already learned this. Okay, now you have to learn this and this. The Laplace transform model and state space model. Your first test will be this, which is coming shortly.
So question, you would just be like, find Z dot.
Now I'm just going to say develop the state space model. I'm going to give you this block diagram, and I'm going to say develop a transfer function or a state space model.
So we don't plug in no numbers.
You can plug in numbers. The numbers will only, so if you plug in numbers, this will become
Yeah, I'm with you.
a numerical matrix.
Yeah, we don't have to do numbers. I feel like
You can do numbers, you will do numbers. Otherwise it will not make sense. You cannot do simulations in MATLAB if you don't plug in numbers. And you need to do simulations in MATLAB. You need to do MATLAB programming. Okay? Any questions? Hunter?
No, this is actually really straightforward.
Yes, it is actually straightforward. You're right. If you do it enough number of times, you'll know it's very, very straightforward. And this is not the focus of this course. You should have been taught how to do this in dynamics. You should come with this knowledge.
We know how to do the matrices and whatnot, but some of this is.
What I'm trying to get to is, if you're given a physical system, okay, you should go from that physical system to generating a block diagram, representing that in a block diagram. You cannot always do exact drawings, right? You do. That's the reason you do block diagrams.
I mean, we did block diagrams. We just didn't do it in the sense of using Laplace transform and changing the domain.
Right. So you do the block diagram, and then given the block diagram or the free body diagram, develop a dynamic model.
I do, of course.
Mm-hmm.
Were you going to do something with that y equals that matrix?
No, we're done.
That is here. I've just put it here.
We're done.
It depends on. So here, it will depend on what is your output. If my output was only this, how would this matrix change?
It would just be one of those. There would be like 1, 0, 0.
Right. Right. It will become 0.
Good.
Okay.
So for y and orange that you got written there, it's just CZ, so don't worry about du. Don't worry about du.
Don't worry about du. Yeah. So here it is like this. Okay.
Sir.
This will be a major part of your first exam. Okay.
When is our first exam?
Dude, he
I
already
think
told
I've
us.
given you the dates.
He's giving us the date.
February 4th, I believe.
Oh, that's right.
Let me double
Not
check.
4th, 5th maybe.
You say you about move it, doctor, Sunday. But I mean, it's nowhere near that date anyway. So it's
Do we? So we need both of those matrices
Yes,
on the final product.
February the
yes,
5th.
yes, you're right. So we need,
Okay.
see, this will tell you only dynamics, okay? This will tell you, for example, when you're looking at this, ultimately this will not help you solve a control problem. What will help you solve a control problem in this is extracting. So here keep in mind, A is just a set of equations defining the dynamics. You need to extract transfer function using Kramer's rule. Okay, and we discussed this extracting transfer function using Kramer's rule in the last class. This is similar to extracting the transfer function. Okay. Again, here too, if you just write these represents the dynamics. Okay. So what you do with what is the transfer function equivalent of here? Try to understand. This will only tell you the dynamics. What is the dynamic relationship? Okay. Your task does not end there as an engineer. What is your ultimate task?
You want to find displacement.
You want to solve for x1 of t, x2 of t for these using differential equations. Solution to differential equations. You want to solve for, again, x1 of s, x2 of s here. You want to solve for one of these outputs here as well. How that is going to vary as a function of time and frequency. That's what your ultimate interest is. And what is triggering all of this? What is triggering the dynamics?
Space.
Huh?
Space.
The force.
Force. You define a force. Force is under your control in that you can select what kind of force, right? You can have different types of forces being applied. It could be, and we look at force equation, we can look at how is force varying. What is force varying as a function of?
In this case, time.
Time. Okay. So force is varying. Here it is varying as a function of time. Here it is varying as a function of
Speed.
frequency. S is frequency variable.
Frequency.
Keep in mind S is frequency variable or the last variable. Here it is varying as function of time. Here it is varying function of frequency. Here is varying as function of frequency. Sorry, time. Okay. All right. So please pass me your attendance.
Brian, I'll put your name. They keep your office paper there.